Hello friends and welcome to the Power Electronics course in the Electrical is Easy channel. So in today's class we are actually going to draw the turn on characteristics of the power diode. So the idea what I have in giving this lecture is that we will start with the ideal case of diode and slowly we will introduce non-linearities in the power diode and we will add on to this graph so that in the final graph you will actually understand what is the turn on characteristics. So before starting that, we have seen some equations in the previous video, that is for the diode in the reverse bias condition and the diode in the forward bias condition. So we have basically written the value of ID and VAK for the ideal case and the practical case. Similarly, in the forward bias condition, we have written the values of VAK, ID for both the ideal case and practical case. So let's start with the first graph, that is for the ideal case of the power diode. Ideal case of the power diode. Now in the reverse bias condition, see in the reverse bias, the ID value will be equal to 0, right? ID value is equal to 0 and VAK value is equal to minus Vs, minus Vs. And in the forward bias condition, VAK value is equal to 0 or V forward will be equal to 0 and ID value will be equal to Vs divided by Rs. Okay, all these things we have already derived. So let's put it in the graph now. So already drawn the input graph. So the input I told you, this is turn on characteristics. Therefore, the diode will be going from the reverse bias condition to the forward bias condition. So we are applying the voltage from minus Vs to plus Vs. So let's start by drawing the value of ID. So ID value you can see in the reverse bias condition is 0. So let me just draw that. ID in the reverse bias condition is equal to 0. ID in the reverse bias condition is equal to 0. And ID in the forward bias condition, see after this, let us call this as time t0. After t0, ID is equal to Vs divided by RL. So I can just draw like this. So this is Vs divided by RL. ID is equal to Vs divided by RL. Now let us draw the value of VAK. So VAK in the reverse bias condition is minus Vs, right? So VAK in the reverse bias condition is minus Vs. Sorry. VAK in the reverse bias condition is minus Vs. So this is minus Vs. After T0, that is when the diode becomes forward bias condition, VAK value is equal to 0. So the graph will look like this. So this is a simple turn on characteristic for the ideal case of the power diode. So now we will add some non-linearities to this. So let us add some non-linearities. So namely, I will be adding two non-linearities. One is the concept of reverse saturation current. Reverse saturation current. Okay. And next is the concept of that VAK is not equal to 0 at the forward conduction. Right. So these are the two nonlinearities. In the practical diode, you know that there will be reverse saturation current and also VAK will not be equal to 0 at forward bias condition. So in that case, in the reverse bias condition, I can write ID will be equal to minus Is, right? The reverse bias condition for practical case, ID is equal to minus Is, okay? And VAK will be as usual, VAK is equal to minus Vs. And forward bias condition, the ID will be roughly equal to Vs divided by RL, almost equal to Vs divided by RL. But the important thing here is that VAK will not be equal to 0. VAK will not be equal to 0. So again, I have drawn the graph. Let us draw the value of ID. So ID in the reverse bias. So this is the reverse bias condition. This is the forward bias condition, right? So ID in the reverse bias condition, let us see. ID in the reverse bias condition is minus Is. I will draw it like this, right? So this is minus Is. After T0, the diode going to forward bias condition. So in that case, in forward, see, this is for reverse bias and this is for forward bias. In the forward bias condition, ID value is equal to Vs divided by RL. So I will draw like this. So in the forward bias condition, ID is almost equal to Vs divided by RL. Almost equal to. And this is minus X. Now let us draw the value of VAK, or let us draw the graph of VAK. Now in the reverse bias condition, VAK is equal to minus Vs. We are taking it directly like that. So VAK is equal to minus Vs. I can also write it as almost equal to minus Vs, but for all practical purposes, it will be equal to minus Vs. Okay. Now, important thing is the forward bias condition. In the forward bias condition, earlier case VAK was equal to 0, but in this case VAK will not be equal to 0. It will have a finite value. right? It will have a finite value, and we can call that VAK will be equal to V forward voltage. V forward voltage. Okay, V forward is the VAK in the forward conduction mode of the diode. Okay, so we have added these nonlinearities and we have drawn this graph. Now in the third graph, we will be adding some more nonlinearities. So here we have added two nonlinearities, that is reverse saturation current and VAK is not equal to 0 at forward conduction. Now we will modify or we will add two more nonlinearities, that is we will add now to protect the diode from sudden current surges. Okay, to protect the diode from sudden current surges, usually an inductor is placed in series. Usually an inductor is placed in series. Okay, so such inductors are called di by dt current limiting inductors. Di by dt limiting inductors. Okay, and the fourth nonlinearity that we are going to introduce is that, see, this is the diode in the reverse bias condition. I have drawn it here. So you can see the depletion region, it is very big. Okay, wider depletion region. But in the forward bias condition, the depletion region is almost negligible. That means these charges has to evaporate and come back. These charges has to become in this format. Okay, so this is not instantaneous. It will take some time for the depletion region to reduce its width and come to this small width. Okay, so the change in the depletion region, change in the depletion region is going to take some finite time. Going to take finite time. It's not instantaneous. So we are going to take that also into account. Okay. Now, the impact of dA by dt inductors, what does an inductor do? The inductor does not allow sudden changes in current. It only allows the current to increase gradually, right? So ID can increase, ID can increase gradually. Okay, and change in the depletion region from finite time. So in this case, what will happen? In the reverse bias case, the voltage was minus Vs. The voltage was minus Vs. And in the forward bias case, the voltage I took is V forward. V forward. And if you look at the previous graph, that jump is also like instantaneous, right? In reverse bias case, the voltage was minus Vs. In the forward bias case, I told the voltage is VAK is equal to V forward. That is also instantaneous. But this will also take some finite amount of time, right? So the transition from minus Vs to V forward, okay, will take a finite amount of time. Will take a finite amount of time. Okay. So now let's start drawing the graph considering all these nonlinearities that we have set. So let's start by drawing the value of ID. So here the diode is reverse biased and in this area diode is forward biased. Let us take this time as T0. That is the switching from reverse bias to forward bias condition. Okay. So now in the previous graph, if you see here the reverse bias condition, the current was minus Is, and after T0, that in the forward bias, it quickly jumped to ID is equal to Vs divided by R. Now I told you, due to the inductors, the current will gradually increase, right? The current will gradually increase. So the current is almost going to increase something like this. So this is how the current is going to increase. So that is what I am going to draw the graph. Okay. So in the reverse bias condition, the current value is minus Is. So that I will put here. Current value is minus Is. And in the forward bias condition, the diode current gradually increases and finally becomes the value ID is equal to Vs divided by R. ID is roughly equal to Vs divided by R. So it takes finite time, and the reason for this is the current limiting inductance. Okay, and also the lead inductance, that can also be a reason cumulatively due to the lead inductance and also the current limiting inductance. So I'll put that here. The lead inductance and the current limiting inductance, due to all these factors, ID is roughly equal to Vs divided by R. Now let us draw the value of VAK. Okay, so VAK in the reverse bias condition we have already drawn. That will be equal to minus Vs. Right, the reverse bias condition is called, it is equal to minus Vs. Now in the previous graph, I have already shown you, when the diode is forward bias, the depletion region needs some time to reorient or reconstitute itself from this configuration to this configuration. Therefore, the voltage decrease will be gradual. It will be like this, okay. So in that case, what happens is that the decrease in voltage will be gradual, right? Something like this. But once the diode turned on, I told you this value will settle into VAK is equal to V forward. But in this case, I am assuming that there is conductivity modulation is already set up. But the conductivity modulation also needs a definite amount of time. The conductivity modulation also needs a definite amount of time. So that means initially the conductivity modulation is not fully set up. Okay, when the conductivity modulation is not fully set up, the conductivity of the drift region will be less. Okay, therefore R drift, the resistance of the drift region will be high, or I can tell the on-state resistance of the power diode will be high. Okay, initially when the conductivity modulation is not fully set up, or I can tell that the power diode, or not the power diode, let me tell the drift region has resistive nature. The drift region has resistive nature. That means the voltage VAK, I told you, which is equal to VJ plus V drift region, right? VBR. Okay, VAK is equal to VJ plus VBR. Where I told you this VBR is equal to IF into R on. IF into R on. Okay, so initially this is purely resistive in nature. This is purely resistive in nature. Therefore, VAK also is going to follow the same pattern. So when it is resistive in nature, okay, when it is resistive in nature, you can see that VBR is proportional to IF. That means when IF increases, right, VBR would increase. VBR would increase, and if VBR increases, naturally VAK also will increase. VAK also will increase. So an interesting thing is going to happen here. You see, the current is increasing. The current is still increasing. The voltage is here. The current is still increasing. Initially, I told you the voltage will settle in at V forward. Okay, something like that. It would have settled at this value. But here, conductivity modulation has not set up till now. Okay, so as the current increases, the voltage also increases. The voltage increases like this continuously and settles in at a voltage which is called V forward. V forward. Okay, this is the voltage. I can also as reverse the forward recovery voltage. This VFR is called forward voltage. Now, but after some time, the conductivity modulation, double injection, all those phenomena will happen after a certain time. So conductivity modulation is going to set in. That means the conductivity of the drift region is going to increase, right? The resistance of the drift region will decrease. I can tell the on-state resistance will decrease, right? The on-state resistance will decrease. That means VAK naturally it would decrease because R on is going to decrease. R on is going to decrease. VBR would decrease. Naturally, VAK also would decrease, right? R on is decreasing, VBR is decreasing, and therefore VAK will decrease. Okay, I'll write that here. R on is decreasing, therefore I can tell VBR would decrease, and once VBR decreases, VAK also decreases. Therefore, beyond a certain time, what happens is that this graph would actually come down. The VAK graph actually comes down, and once the conductivity modulation is fully set in, this value we can call it as V forward. This value we can call it as V forward. Okay, and this voltage peak that you see, is called forward recovery voltage. Okay, this is called forward recovery voltage. So that's a very interesting point of this graph. So I have written some notes here. You can take a screenshot if you want. So initially, conductivity modulation has not set up completely. Okay, so drift region is resistive in nature. So as ID increases, V drift increases, or that VAK increases, right? And VAK peaks at a voltage VFR, right? This is the peak voltage VFR. VAK is equal to VFR is the peak voltage. Now, as ID increases and becomes close to IF, okay, IF in the sense I can write it as ID is roughly equal to Vs divided by RL. Conductivity modulation fully sets up. Okay, so when conductivity modulation fully sets up, that means conductivity is increasing, right? The on-state resistance will decrease, V drift will decrease, and therefore VAK also will decrease. Okay, and I told you VFR is nothing but the forward recovery voltage. Now, this VFR is significantly higher than the steady state voltage drop across the diode at forward current. You can see this is the V forward, right? This is the steady state drop in forward condition, this small value. But you can see that this VFR is significantly higher. And in some cases, if you are not careful, this can even damage certain circuits. Okay, so that is very important. You can have marked two time here. So this total time is the from to this point, from the recovery stage to the steady state stage, time as TFR, or you call it as TFR, you call it as forward recovery, forward recovery time, forward recovery time. Just like reverse recovery time, this is forward recovery time. Now usually this forward recovery time, this is equal to T1 plus T2, is equal to T1 plus T2 here. This time is much less than TRR, or the reverse recovery time. Okay, so usually less significance is given to these circuits here, but still it is a very important concept to understand. So I hope today you have understood the turn on characteristics of power diode. Turn on characteristics of power diode. So this is the actual turn on characteristics of power diode. One very step by step in understanding this. We started with the ideal case, we introduced some nonlinearities, we introduced some more nonlinearities. Finally, we introduced the concept of conductivity modulation. So once the conductivity modulation is fully set up, that is at this point, you see that the voltage has fallen. And in this case, you can see the conductivity modulation has not set up. Therefore, you can see that the voltage is actually increasing due to the resistive nature of the drift region. Okay,